Work and energy summary. Work is defined as the force exerted parallel to a displacement. If you have a constant force, we use this expression right here, where work is a dot product of your force and your displacement, or the magnitude of force times the magnitude of your displacement times cosine theta, the angle between the force and the displacement. If you don't have a constant force and it varies with position, then you use this integral over here, where you integrate from your initial position to your final, and you're taking your force, your equation for force, dx. Now, when you have work done by an external force, that will change the energy of a system. And we represent that by the work-energy equation, which is work equals final energy minus initial energy. And typically what we're dealing with is the kinetic energies if the potential energy stays the same. We can calculate a potential energy, and the symbol for that is U, capital U, for a system where the system's objects interact via a conservative force, f of x. In that case, the potential energy is the negative of the work done by this force, the force of the field, or if you have a spring, it's the force of the spring. So that will be the negative integral from your initial position to final of f of x dx. What if you were to take the derivative of both sides of that equation? So where you have u is equal to minus the integral of f of x dx. Well, you have du dx, then you have your derivative of the integral, and mathematically, a derivative cancels out the integral. It's not the most rigorous way to say it, but it works. So we have this very valuable equation. The derivative of the potential energy is equal to minus the force. A conservative force, as shown on the previous slide, it has the following properties. The work done by a conservative force on an object depends only on its initial and final position. It is path independent. The work done by a conservative force on an object is zero when you have a closed path. That's when your initial and final positions are the same. And then we have these three energy equations that we'll be using. Kinetic energy is 1/2 mv squared. Gravitational potential energy is mg delta h. And elastic potential energy is 1/2 kx squared. And that's for a perfect spring where f of x equals minus kx. A particle could be in equilibrium in two different types. One is stable equilibrium. That's when you have a stationary particle, and if you just push it away a little bit from its position, a force will act to return it to its original position. The potential energy U of a particle in stable equilibrium is a minimum. On a potential energy versus position graph, the particle will be located at the bottom of a concave up curve. So what you'd have is something like this, where this is position, and over here would be your potential energy. That is stable equilibrium. Unstable equilibrium, that's when you have a stationary particle being pushed away from its position. A force will act to keep it moving away from its original position. In that case, the potential energy is a maximum. On a potential energy versus position curve, the particle is located at the top of a concave down curve. So let's see what that would look like. Here's the curve. This is your position. This is your potential energy. Particle located here would be an unstable equilibrium. And that is a maximum potential energy right there. Power is the amount of work delivered over time. And we can have average power, which is where we have the change in work over the change in time, or instantaneous power, where we take the first derivative of work with respect to time. There's a handy equation relating power to force, and that's power is equal to F dot velocity, which again would be the amplitude of the force times the magnitude of the velocity times cosine theta. Now you can solve for either instantaneous or average power. Just be sure to be consistent. So if you want average power, you have to use average force and average velocity. If you want instantaneous power, you need instantaneous force and instantaneous velocity.